Hi there, welcome back. Welcome back to another video in the Magnecorder restoration. If you've watched my channel for any length of time, you'll know that I always harp on about learning. It's always a learning experience. And this time I learned something else, which has nothing to do with the technical side. It's got to do with the creation of YouTube videos and what you say on them. What I've learned to do, or not to do, is to mention easy, quick project, short videos, things like that, because for some reason it always comes back to bite me. And this one is a perfect example of that. I mentioned in the previous video, that it looked like it was going to be a short one. It's going to be an easy one. There's not much to it. And well, here I am eating my words. You've probably gathered from this introduction, this preamble, that this one caused a few hassles I wasn't expecting. And the reason is that, very simply, this thing is incredibly well built with very, very bad resistors. The rest of the components, well, the capacitors were replaced. I've done all that. No big deal there. I was expecting those to be leaky, so that was not a surprise. But the part that I was not expecting was that practically every single resistor had to be replaced. Now that in itself is not too much of a challenge. I've done that before. The problem here is, and we're back to why this thing was so well built. The problem here is that there's very little space in there, and getting to some of those components was very tough. The resistors they use on here are the carbon comp, and some of them are the pretty hefty ones, which means that the leads are very thick. Now, when the leads are thick and they perfectly tie down into the solder points, in other words, they've been mechanically tied in, crimped in, and then soldered, which is the way you're supposed to do it. You're supposed to do a mechanical fix before you do the soldering. The soldering is just to make sure it stays there and to complete the connection. When you do that, trying to desolder some of these is incredibly difficult, especially when you don't have much space in there. And that's what happened here. Everything is very tight on some parts of this chassis. And so getting to some of those components proved a true nightmare. I actually timed, on one occasion, I spent almost an hour trying to replace one anode resistor. Okay? One resistor. Now, that makes me incredibly slow, or it makes those things incredibly tough. Probably a bit of both. But anyway, I'm waffling on again. What have I done here? Well, I have replaced all the resistors that need replacing. I've checked all the components that need checking. I have replaced the Selenium rectifier. I'm going to show you that in more detail next. I have now got to the point where I'm ready to test it. But before doing that, I'm going to just recheck everything. Okay? So in this video, I've got to warn you, we will not be doing an audio test. And I'm loath to say that it'll be in the next one, but I think it will be, unless something really unexpected happens, and it usually does. So I'm going to just carry on and show you what it is that we've done here. So starting with a quick overview, as you can see, quite a lot has changed. You can see a lot of new components on here. There are a few of the originals. I'll show you a close-up, but this is the Selenium rectifier that's been replaced. There are all those resistors in the output circuit. All those have been changed in there. A lot has been changed back here. This is where it proved incredibly difficult to get hold of everything in there. These two capacitors, I've left the original cans in here. These were removed and completely restuffed. I did consider putting the capacitors on top, the new capacitors on top, and leaving the cans in place. But this thing is fairly tight in here. So I did the old trick of just removing the capacitors, ripping out the guts, restuffing them with new capacitors. This one here is 2 by 20. I put 2 by 22s. So instead of 2 by 20 microfarad at 450 volts, this one was originally 85 degrees, I think it was. Yep. I now have 2 by 22 microfarads at 450 volts. As you can see, the tops, the connector, the actual solder tags had to be replaced. So everything is new in there. This one, I did a similar trick. Same story, ripped it out, ripped the guts out and restuffed it with 3 capacitors. This one has got a 10 microfarad, a 15 microfarad, and another 15 microfarad, all of them at 450 volts. Now, the thing about this, I actually thought of putting 22s on everything. In fact, let me correct myself. This thing's got a 10 and 2x22s, okay? The reason I didn't replace the 10 with 22 is I checked the data sheet for the rectifier tube, and they actually give us a maximum capacitance that you're supposed to put into the first filter. It says 10 microfarads. Now that is for reasons of safety in terms of inrush. These rectifier tubes do have a maximum capacitance you're supposed to put in there. The reason is if you put a very big capacitor, the inrush current that comes through can blow the filament or can blow the actual anode connection, which is a very thin wire. These rectifier tubes, this is a 6x4. This thing's rated for lowish voltages, not higher than 400, and this is fine. This one's 350 something. So that's within spec, and it's also rated for a maximum of about 70 milliamps. So it's a sort of fragile tube, and you have to take care that you don't overload the first filter by putting in a huge capacitor in there. So that thing's a 10 microfarad, and I stuck to that. And here's that part of the circuit. Here we have the rectifier. Out of the rectifier, we're supposed to get about 354 volts. We then go to the first filter cap, that's the 10 microfarad. And again, the reason is because there's no resistor between that point and that point. When this thing starts conducting, it immediately starts to charge that capacitor. And because it's a very low impedance path, you don't want this thing to look like a short or a big short, if there's such a thing. So maximum capacitance there is 10 microfarads. That's the one I mentioned. It's connected to 2 other caps, that one and that one. And according to, on the schematic, they don't mention what it is, but according to what's on the can itself, those are 15 microfarads. At the moment, I've got 22 microfarads in there, which is fine, because it is not directly connected to the cathode of the rectifier tube. Then from there onwards, it breaks up. It actually tapers off. There's a 1.2K resistor. That's a big resistor, one of those 3 big resistors we have on there. That is perfectly all right. So that was cleaned up and put back. That goes to that point, which meets another 20 microfarads, in this case a 22 microfarad in the first can that we see in line there. And then it goes off to there. As I mentioned in the previous video, on record, it supplies that connector. And on playback, it actually goes through a 25K resistor, again, one of those big brown ones. The reason is to provide a current path to ensure that, I believe it's to ensure that the voltages here stay more or less stable. Okay, so that's one cap, and that then is part of that second one. It goes through a 2K resistor, again, one of those big brown ones, which is fine, and it creates our second B plus over here. So as far as the power supply is concerned, that is what we have done. What else can I tell you? Oh, there is one other resistor that was fine, one of those big ones there. Smaller, but still quite big, 4.7K. That takes us to our third B plus. Remember this B plus, this one here goes nowhere by itself. It provides this line and that line, but this is the real first B plus that goes through the primary of the coil to the first anode. And then it creates a second B plus here through that 4.7K, where it meets another 22 microfarad capacitor in this case. A 47K resistor, which was burnt out, or rather completely out of spec. So it was replaced, and we get our third B plus, which is then filtered by this capacitor. So we've got all our B plus lines done. And in this particular section, we replaced the multi-section can, that one, 3 capacitors. We replaced that one, 2 capacitors. And we replaced 1 resistor so far. That one there was that first resistor that I found across the actual multi-connector, which was open, so that was replaced as well. So that sort of took care of the power supply section. Now, This job of changing or stuffing the capacitors is quite tedious, but in this particular case, it's worth it. I needed to make sure that I had a very, very good supply, and reconditioning these caps, or putting this under load and letting the leakage repair itself was just not an option. You can probably see what's coming next. Everything in red has been replaced, but I'll take that one step at a time. Then I went and did the Selenium rectifier. This is the original Selenium rectifier over here. I wanted to replace this. It's a bridge rectifier. And to do that, I removed it from here and I rewired in one of my little boards. If you've seen a couple of videos ago, I did a little project where I built these little boards. Basically, it's a board for a bridge rectifier using 4 diodes, and you can put 3 resistors in series on the output. The reason is to reduce the voltage of this. This thing has quite a high voltage drop, which the bridge rectifier with silicon diodes does not. This thing would normally have a voltage drop of about 1.4 volts or 1.2 volts. This thing probably more like 8 or 10, I'm not sure. But I leave that in there, I put that in there and left the resistors open. So this thing is not supplying yet. I have to put a resistor in there. Yeah, I'll put a link above and you can see the whole logic behind that little board. And the idea is that I can then adjust this so that I can drop the voltage that I need so that the circuit that exists there will give me the 12.6 volts that I need for the heater windings. There is one capacitor in that circuit, in the heater circuit, and that is a 1000 microfarad 25 volts. There is a filter can on the bottom, which is the third filter can, which again proved almost impossible to remove. That one, because it's only one capacitor, I decided to fit the capacitor on the top side here. This is a Nichicon 1000 microfarads at 50 volts. It's pretty nicely stuck in there. The original has been cut out of the circuit, so we've got our filtering for the heater winding as well. The Selenium rectifier has now been replaced with 4 silicon diodes. So the voltage here will be quite a bit higher than it was before. So the idea is that those resistors will be fitted on this line here, in line, in series. We'll work out how much we need when we do the testing. And now we come to the crazy part. This whole section back here is where all the anode resistors, the 100K resistors that link the anodes of those triodes to the B+ were fitted, as were all the capacitors, which were obviously needed replacing, the paper caps. So this is the one that proved a real bummer. There are a couple of electrolytics on here. These are the cathode bypass capacitors. They were replaced, and obviously they're a lot smaller, which helps a little bit. So by removing those and putting smaller caps in here, when I say small, I mean physically, the value is 22 microfarads. The one that was there was 25, so same thing. All the resistors, the cathode resistors replaced. These are actually low power 600 milliwatt resistors, which is fine. There's not that much current going through there. I left the one resistor in there. There's actually one there that didn't need replacing, but it's actually one which was not in the schematic. And I noticed that it is in place and there's a good reason for it. But anyway, the other mess is down here, and I had to make sure that I rebuilt it without it being a mess. So this is pretty well done, but you can hardly see it. There are 1, 2, 3 capacitors down here. These are the coupling capacitors. There are all the resistors. There are 3, 4 100K resistors on there as well. And there are the 1, 2, 3, 4, I think it is, cathode resistors, 2 cathode bypass capacitors. Yeah, and that all fit in there. And I did the cleaning at the bottom before I put those components in. And I had to put some heat shrink, make sure that nothing was touching, because this is very, very tight down there. In some cases, because of the way the original components were wired in and really bent in there, I didn't want to damage the tube sockets, for example, the solder tags on the tube sockets. So I used the little sort of wrinkly wire thing, the trick where you take a component, put a little coil on the end, fit it over the top and solder it. And that allows you to not strain the contact point. Well, you don't strain it much, but it still provides a very, very good connection. And this is what we're talking about. All these resistors were swapped out. These 100Ks here, these are cathode, or rather the anode supply resistors from the B+. So that's a 2-watt resistor, 2-watt resistor, 2-watt resistor. The others were 600 milliwatt. So these here, these are all just signal, audio signal, not a problem. This one here is the cathode resistor, bias resistor for that triode, and that one there as well, and that one there, and that one there. This one was I actually used a bigger resistor. This is 820 ohm. The 12AU7, which is what this tube is, contrary to the 12AX7 up there, this one actually passes quite a bit more current. So I wanted a heftier cathode resistor here so we don't have heating problems. If at least on power up, it might actually overheat a bit. Yeah, and the rest here, these are just controlling the meter and the monitoring and the monitor headphones, so no big deal. These capacitors were all changed to film caps, as you can see. This one here, there's an error. The resistor that was on there is 470K. It makes more sense as a grid resistor to this particular triode than 47. So that was replaced with a 470K. There was one other error, and that was here. This thing had, from the wiper of the pot, which was fine by the way, there was actually a 227K resistor as a grid stopper to the grid of this tube. And that one was left there. This was actually one of the few resistors that was fine. This one and this one, these were fine. So they are still there. And other than that, okay, that sort of covers that part that I've just described to you, which this thing looks so simple. It does. It's deceptively simple. You look at this and you think, oh, you know, half an hour, two. This thing is taking me nights. So I have great respect for the builders of this device. They built it incredibly well. Unfortunately, the components didn't last as well as the soldering. Anyway, onwards. This is where things got a little bit strange. This is the output stage. That there is the 600 ohm balanced output connector. These resistors were in here, or there were two resistors in here. That resistive network there was in place, sort of. And they've got a set of values on the schematic, which is 330 shunt, 180 series. So 180, 180, 180, 180 with the 330 shunt. That to me looks like a typical H-bridge attenuator. I'll describe that on the schematic, but what we had here is none of these resistors matched what we supposed to have, what we have on the schematic. The two resistors coming from the output transformer, instead of being 180s, that's that one there and that one there, were actually 330s. Which left me a little bit perplexed, because then they've got a shunt resistor here, which according to the schematic, they've got 330 ohm, and what they had here was 3.9K. And then these two were also 3.9K each. That did not make sense at all. Now what I did find is I found a schematic for another model of this, where the 600 ohm output, 600 ohm impedance output, is actually wired with 2 by 330 ohms with ground at the center, and then the two ends go straight to the output. And that might be what they've had here. And someone tried to put a pad. They didn't quite do it. They didn't replace the two resistors that were on that line there. These two resistors, by the way, are now pretty visible, but they were somewhere on the underside, very difficult to reach. In fact, very difficult to see. So someone might have changed this around from the original wiring to what they believed was going to give them the impedance drop that they, or rather the attenuation they wanted. So at the moment, what I did is I looked at some calculators on the web, and the calculator that gives us 180 ohms here, 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 and a 330 ohm there is actually a calculator for 12 dB of attenuation. That's what this thing is set for. If we want to change it, we can then just look at what resistor values we need, and we can replace it then. So this is what we have on the schematic. What we have there now is exactly what's on the schematic. 180, 180, 180, 180, 330. This is a typical H-bridge or H-pad attenuator, and these resistor values are for 600 ohm input impedance, which is what I expect is wanting to be seen there, 600 ohm output impedance, which is what it says that you're producing, with a 12 dB of attenuation. These values correspond to 12 dBs of attenuation with equal impedance in and out. Few things I'm not sure of. I'm not sure that that is 600, but I expect it is. And I'm not sure that 12 dB of attenuation is what they were trying to achieve here. Because what we had was not these resistor values. The only value that, in fact, none of these values were on the device itself. What we had there was 330 here, 330 here. And then these three were 3,900 ohms, 3.9K each, which means I don't know what impedance they were trying to achieve and what attenuation they were trying to achieve, or whether they just made a mistake. That could also be the case. If you go to some of the websites that give you the calculations for these things, it's easy, but you've got to know what you're doing. Otherwise, you can get yourself completely bogged down and create errors. For example, these two, if you look at, this is the balanced version. If you look at the single-ended version, this would say 360 ohms. And it might even say 390 ohms because that'll be the closest standard value. And someone might think they're putting 390 ohms when they're putting 3,900 ohms. All sorts of reasons may have crept in there for that error to have occurred. I don't know. But this is what we have at the moment. Another thing is that I saw in a previous schematic with this sort of transformer, I'm not sure if it's the same transformer, but what they had was from here, you had a 330 ohm. From there, we had a 330 ohm, not this one, but that one there. And these two would join up and go to ground. And then the output, the 600 ohm output, would actually come from those two ends. Maybe that's what they had and they wanted to correct it, adjust it for attenuation. I'm not sure. I think that might be the case because these two resistors that were in there, these 330 ohm resistors, they were incredibly old. They were buried in the back. They'd never been really changed. Maybe the connection point had been broken, which would have been ground and ground, so they can put this shunt resistor in there. I'm not sure, but at the moment, this is what we got. And these are now very easily accessible, and we can reach them and change the values if we want to change the attenuation values. All right. And as you can see, it's sort of painted and it's not finished. And this is why I'm not going to test this thing today. I want to make sure everything is wired properly. Make sure there's no shorts. Make sure I haven't created any cock-ups in some of the soldering I've done. I'm not opening this up. This thing is there as is. I want to check the switches again and the wiring, but I'm not opening this up. This is a filter unit with two different tapering filters for 7.5 inch per second and 15 inch per second. So these are basically equalization filters. I don't know what's inside that can. I don't want to jinx it by opening it up. We'll test it. When we test it, we'll find out if it works well enough. We've also got some testing to do here. I need to make sure these connections are working properly or made properly. I believe I found another mistake here somewhere. There is an error in the schematic and I haven't corrected it. I want to test it. I haven't corrected the actual schematic because I'm not sure exactly what the error is. I do know that this point is directly connected to ground, which makes sense. It's the secondary. And what else can I tell you? Well, not much else except that this thing is nearly there. I'm tempting fate again. So in conclusion, for this particular video, I have to check all the wiring on here. I have to do a bit more cleaning. Some of these sections have not been cleaned properly. The outside has not been cleaned at all, except obviously for these filter cans, which I cleaned when I restuffed them, and the underside there, obviously. But there's quite a bit of cleaning to do here. The faceplate needs cleaning, and then I need to put this all together, make sure all the switches are working exactly as they should be, and then I'll be able to do a final demonstration video. Hopefully without any more mishaps along the way, without any more unforeseen circumstances along the way. So once again, I want to thank you for your patience. Thank you for accompanying me in this restoration of this relic. It really is an amazing piece of equipment. I love working on these except for trying to get the solder connections off. That's all part of the challenge. And again, thanks for watching. Bye for now and stay safe.